Hello. Our CSE 527 final presentation is about detecting deepfake videos and generalizing the neural network model to detect fake videos from multiple domains. Our team is JonathanBoyack and SangyupLee.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. That's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward in the age of information is going to be the difference between whether we survive or whether we become some kind of fucked up dystopia. Thank you, and stay woke, bitches.
This video was made using the deepfake model, but it appears to be authentic. This was a video where Obama curses at the audience. The facial expressions and natural movement are from the original actor Jordan Peele, as it shows later in the video, mixed with Obama's own movements. As this video explains, the importance of identifying fake videos is crucial for verifying information and keeping the trust of your audience. Were you fooled by this style of fake video? In this presentation, we will discuss the importance of detecting manipulated videos by first giving a brief introduction and overview of the issue. We will then speak about the problem that we are addressing in more detail and explain the method that we use to tackle the problem and solve the issue. After that, we will take a look at the results of our work so far and explain what issues we are still facing and why those are still persisting. We will then show a demo of what we are working on and transition to talking about what work still needs to be done on the project. Deepfake videos may seem fun and harmless, but with realistic-looking, hard-to-detect, counterfeit videos that are easy to create being shared on social media platforms, misinformation can spread quickly and easily. This propagation of untrue information can become a serious problem. Deepfake has created a method of facilitating this and other more important issues. Socially, people can create a fake video of a friend or colleague doing or saying something that could get them in trouble with other people or even at work. Or they could share a video of a celebrity saying something that they never did, like that video of Obama we just watched. Legally, other problems can occur, such as being able to create a video to scam others into believing something untrue or tricking them into doing something that appears to be legitimate. It is difficult to prosecute the perpetrators when the victim may not have any idea of the faked video. Now, falsifying a voice is possible with deep voice, which can end up hurting the victim even more. Stopping the spread of faked videos is becoming very difficult due to the sheer amount of videos that are uploaded to social media platforms daily, as well as the time it takes to correctly identify if a video is fake or not.
For our project, we considered 3 different kinds of deepfake generation methods. For example, if you see the 2 photos on the left side, these are real frames from a video. Using these 2 videos, we can generate 3 different fake videos by using deepfake, face-to-face, and face swap. First, for deepfake, the method replaces the target video's face into the source's video's face. If you use face-to-face, it captures the source's facial expressions and natural movements and replicates them onto the target. By keeping the target's face, it only replaces the target's facial movements with the expressions from the source. If you look closely at face-to-face generation, in the original photo the man has his lips almost closed, but in the manipulated face-to-face photo on the bottom, his mouth is open just like the source actor. This method is the hardest to detect by human's eyes. Lastly, for face swap, it is similar to deepfake in terms of replacing the target's face with source's face, but has a lower quality which makes it easier for humans to spot. So, can we detect these videos with computers? Yes, we actually can. There is research already done in this area from the Technical University of Munich called Face Forensics++. They introduce face-to-face fake videos and how to detect those fake videos. They utilize a CNN-based deep learning model to detect the forgery, and the accuracy is quite promising. However, the problem with this method is that the model is trained to identify only one method, for example, face-to-face. This model is suitable for detecting face-to-face fake videos, but not on a different video manipulation methods such as face swap. By looking at the picture table on the right, the leftmost column 4 pictures are the manipulated video frames using face-to-face and face swap. The middle column is the activation map from the face-to-face trained detection model, while the last column is from the face swap trained detection model. Neither one of the models was able to detect the fake from the domain that had not been trained. In this perspective, we might have this question: can one model detect multiple fake video domains? Yes, this work is also done by the same team from the previous work. They detected 2 different fake video generation methods with only one model using transfer learning. This picture table shows the fake activation map of the transfer learn model. The left column shows the detection activation map of face-to-face frame, and the middle and right column illustrates the map of face swap frame. It successfully detects both domains. The interesting thing about this work is that they used a minimal dataset to transfer learn a new domain. The importance of this work is then that in reality, new methods that produce fake videos are developed rapidly day by day, and it's rarely the case that we can get good amount of dataset of those new techniques. The importance of this work is that in reality, new methods that produce fake videos are developed rapidly day by day, and it's rarely the case that we can get a good amount of datasets of those new techniques. However, this work only provides one-to-one or multi-to-one transfer learning results. Our research problem for this project comes from this issue. What if we transfer learn more than 2 different domain methods? We wanted to test the efficiency of transfer learning and see if solving this problem can pave the way for solving the model generalization problem. In this slide, we show our full pipeline of detecting one fake video domain. First, we divide the videos into frames and then crop the face region to focus on the faces and excluding the background. Then we label them as fake or real, which is then passed to the CNN-based model for training. For now, we only tried ExceptionNet model, which performed the best among the all state-of-the-art detection methods shown in the Face Forensics++ paper. We used 1,000 fake frames and 1,000 real frames for initial training. The code from Face Forensics++ provides a testing tool using the trained model. We will show a demo video of this tool at the end of our presentation. After obtaining the trained model with one fake video domain, for example, deepfake in this case, we can move on to transfer learning to detect multiple fake video generation methods. Performing the same pre-processing, we train the model again with a very small face swap dataset in this case. When we transfer learn the model, we train the last fully connected layer of the model. After getting a new model, we tested the domains that we trained on, and repeated this procedure until we reached 4 domains. The 4 domains consist of deepfake, face swap, face-to-face, and GAN-generated fake images.
In the graph, the dotted red line is the 50% accuracy mark. Anything below that line can be considered to be a random guess and not an accurately made decision on whether the video is fake or not. As you can see from the data, in the first grouping, the third domain always appears to be a random guess, and not an accurately predicted model. This first grouping was created by first training from the deepfake domain, and then transfer learning from face-to-face and face-swap. The second grouping was originally trained with face-swap, and then transfer learning was done from deepfake and face-to-face. This third grouping was initialized with face-to-face and gives the best overall accuracy for the original 3 domains. This is why we also tested adding a fourth domain, which is the GAN-generated images. As this grouping shows, as more domains are added, the overall accuracy from all the models drops, which negates the positives of adding the transfer-learned domain. Our results were not very promising. As mentioned in the previous slide, for the majority of our models, the third domain doesn't work well in determining whether a video is fake or not. We also tried increasing the number of epochs that we trained the data for, and it did not seem to make much of a difference to our overall accuracy. One thing that we were able to learn was that the performance changes based on the domain used for the original training. The best performance that we have achieved so far was with the face-to-face based trained model, and the worst performance was with the face-swapped trained models. Some issues that we still have to look into is changing the amount of transfer learning data, or possibly the initial set of training data. It's possible that if we increase the accuracy of the initial model, the other models could improve as well. Also, our accuracy is based on a frame and not the overall video. If we were to run an entire video, would it pick out more than 60 or 70 of the frames as fake, and thus correctly identify the video as fake, even when missing out on some frames? These are some ideas that still need to be implemented.
Here we introduce a demo of detecting deepfake video on the left, and another demo on the right which tries to detect face-to-face generated fake video with deepfake trained model. The model that is trained with only deepfake fails to detect on face-to-face video. The remaining future work for our project is as follows. Since the performance of the transfer learned model was not promising, we need to try different neural network models. Face transfer paper from the same lab of Face Forensics++ tried transfer learning with the autoencoder model. Not only developing a model with autoencoder, we also plan to develop our own neural network model which can be optimized for model generalization. For the next future work, Face transfer paper tried multi-domain dataset for initial training and transfer with one new domain. This approach is a multi-to-one concept, which can also be a proper measurement of efficiency of transfer learning. For our experiments, we only use 2,000 frames for initial training. We also plan to train with more than 10,000 frames and seek improvements. Thank you for listening to our project. These are the references of those 2 papers, and the result sheet is provided in this link.